one of the most efficient ways to take attendance and get participation. But I just ask, don't do it for other people. Make them come to class, okay? All you have to say is, I'm not comfortable doing something like that. The professor asked me not to do that, and it's okay. All right, so let's talk today. Today we're getting into chapter 2, and this is all about visualizing our data, okay? Okay, and so we can start off with visualizing numeric data. Okay, so we'll first deal with numeric data, and then we'll start talking about categorical data after we get through. Let me just pull up my list of key things I need to make sure I mention. Okay. So as far as numeric data goes, remember, whenever we're talking about data, we're generally talking about data from a sample, okay? Okay. And how many observations does a sample have? What letter do we use to indicate the number of observations in a sample? N, okay? So we have N observations. Okay, and so one way to create a visualization of data is the dot plot. Okay, and so let's say you have your data table. Okay, and you've got rows for each person and columns for each thing, and so these are different people. And let's just take a look at one column, and let's say it is age. Okay. And so you've got age 10, 12, 15, and 18 or something. Okay. So this is just a part of a data table, and there are 4 observations. Okay, so we have n equal to 4 in this data table. And so for a dot plot, basically you just have a number line. Okay. And I'm just arbitrarily starting it at 5. I probably should, actually, let me start it higher than that. We'll say 8, 9, 10, 12. Okay, and with the dot plot, all you do is you just put a dot located at each observation. So you get 1 dot, so your dot plot will have n dots. Okay, and this is just a very simple data set with 4 data points. You can imagine having a more complicated data set with many values, and then you can have lots of dots. And I'm going to get tired of drawing dots here, but okay, and so you can have more observations, more dots. And basically you just put a dot, you have a number line along the bottom. And you just draw dots at the locations where you have data. So far, so good? Okay. And I think we can see, if your data set gets really big, to the point where you've got, hundreds or even thousands of observations, a dot plot will lose its effectiveness because you've got to have a dot for every single observation, okay? So when you have many observations, a dot plot is probably not preferred. Okay? And so instead you can create a histogram. Okay? And a histogram, well, you could make a histogram exactly like the dot plot. Let me just so a histogram looks kind of like a bar chart here. So I could take this and just turn it into a dot plot. I take this dot plot and turn it into a histogram just by kind of turning these into bars, like so, okay? And this is just a very poorly drawn histogram, but basically all I'm doing is I'm turning these into bars, and then suddenly this is now a histogram. But histograms can be also made useful in that you can create bins or ranges for your bars, okay? So you can create a quote-unquote bin, and you will have a frequency, okay? And so, if we were dealing with ages, we could have, 10 through 19, 20 through 29, 30 through 39, 40 through 49, and then we would count how many people in our data set have ages between 10 and 19. Okay, and so maybe we count 6 people between 10 and 19. And we count 10 people between 20 and 29, and 5 people between 30 and 39, and 3 people between 40 and 49. What did I say? Touch off, okay. And so in this thing, we would have a histogram with bars at 10, 20, 30, 40, and 50, and then we would shoot. All right, we'll just do 2, 4, 6, 8, 10. Okay, and so here I got a bar right here that has a height of 6, a bar that has a height of 10, and a bar that has a height of 5, and a bar that has a height of 3. Okay, and so this information is summarized in a histogram here. Okay, so you could have bins that span 10 values like we have here, or you can have bins that just span 1 value. Okay, so or anything in between. So with histograms you can create bins. So that your bars span several values. Is that all right? Yes?
So would it be wrong to make things with dot plot?
It's not, I mean, it's not really something we do. In the computer lab, when you do Fathom and you create a dot plot, sometimes like the stacks of the dots aren't completely vertical, and there's like a little bit of mixing. I would say that's a fairly non-traditional dot plot. Okay, generally dot plots, dots show up for one value. I guess you could do something else. I mean, technically, you can make any graphic display you want as long as you explain it. But I would say that would be kind of a non-traditional dot plot. Wrong? Probably not wrong, but non-traditional. I think on Wednesday we talked about relative frequency tables as well, right? So we could do the same thing with this thing and create a relative frequency table. So let me just shrink this down. So if I added one more column here, okay, and I called it relative frequency, you know, how many data points do I have? I got 6 plus 10, 16, plus 5 plus 3, 24 data points total, right? Okay, so 6 out of 24, my relative frequency here would be 0.25, and 10 out of 25, I don't know what that is, or 10 out of 24, that's 42%, 5 out of 24 is 21%, and 3 out of 24 is like 12%. 13%, okay. Well, everything's going to add up a little bit over 1, but that's okay. And so effectively, my bars are going to have the same height, but I could just change these values to kind of be, what's going on here? You know, 10%, 20%, 30%, and 40%, or something like that, okay? And so, you know, if you want to create a histogram but use relative frequencies instead of the actual counts, that's completely allowed as well, okay? And so you can have a histogram or a relative frequency histogram. And it's really just, effectively, all we're doing is just changing this scale and just saying, oh, I'm going to take all of these numbers and divide them by 24 or whatever, right? We're just changing the scale on the side. Okay, but as far as the height of the bars, those are unchanged because it represents the same data underneath. Good? Yes? No? Maybe? Okay. All right, we also have stem plots, and I would say these, I only see these in statistics textbooks. I haven't really encountered stem plots in the real world. Not to say that they are not useful, but I think they're just generally not, I don't know. People like diagrams that people are familiar with, okay? So let's say your data consists of the values 12, 20, 22, 27, 31, and 33, or something like that, okay? With a stem plot, basically you're going to create stems, and here we're going to have stems for the tens place, and the quote leaf would be for the ones place, okay? So the value 12 is represented by the number 2 in the 1 stem. The value 20 is going to be represented by the number 0 in the 2 stem, or the 20 stem, And the value 22 is represented with a 2, and the value 27 is represented with a 7. Okay, so this row right here, the 2027, represents the values 20, 22, and 27. Okay, so what goes in this last row right here? 1 and 3. Okay, and that's basically it. All right. If you have a lot of values, you might create, you might parse your stem so that there are 2. Like you can double the width of your stems in that you can have so if you have lots of values, you can create, and you know, and this one only goes 0 to 4, and this one goes from 5 to 9, and again 0 to 4 for the first 2, and the second 2 would have the values 5 through 9. So here our 12 would go up there. We would have no values over here. The 20 would go over here, and the 22 would go over here, but then the 27 would appear in this row. Okay, and 31 and 33 would appear there. Okay, and so this is just another. If you have many values, you can split the stems into 2, so they kind of spread out a little bit more. Okay, effectively, if you take a stem plot and you turn it on its side, wait, what's going on here? Stop acting crazy. Okay, this is now effectively like a histogram, right? If I can draw. Something like that. Okay, so if we just rotate this, then effectively it looks like a histogram. Okay, and so these are just simple ways to display numeric data. Later on we will see a box plot, but that's not covered in chapter 2, so we'll save it for later. But these are just different ways to display numeric data. So far so good? Okay, just give me a, if you nod your head, it makes me feel good. All right. The reason why we're interested in all of these like graphic displays, okay, is often we want to describe the distribution. Okay, so you know, describing the distribution of numeric data. Well, what am I? When I talk, I can't describing. Okay, so I think sometimes students get a little bit hung up on the word distribution and what exactly does it mean. Basically, it just means how are the values distributed, right? Are all of the values concentrated around certain, are all of the numbers concentrated around certain values, or are they, you know, spread out all over the place? You know, how are the values or the numbers in our data set distributed? So you can think of it that way, right? Okay. And so with a histogram, you get to see things like the shape of the distribution. All right, so let's, I'm going to draw a histogram that looks like this. Okay, so, you know, here's a histogram. This is, you know, perhaps this is the histogram for height. Okay, so maybe histogram for height. Okay, and so let's do a height of males in the U.S. Okay. Okay, and so, you know, the average height is around 5'9", 5'10", so that's like, we'll just say 70 inches right here, okay? And then if you're a little bit taller than that, like 6 feet tall, then you're over here. And then as you get taller and taller, there are fewer and fewer people who are that tall, okay? On the other hand, you go in the other direction, there are fewer and fewer people who are, you know, less tall, okay? So, you know, basically what this says is, you know, the most common heights for men, as indicated by the height of the bar, is between, or are between, you know, 5'8" and 6 feet tall. Okay, whereas, you know, values, there are people who are taller than that, people who are shorter than that, but as you get further and further away from this range of average, those heights become less and less common, okay? Okay, so, yeah, are there people who are 6'7"? Yes. Are there lots of people who are 6'7"? No. Okay. Are there men who are, you know, 5 feet even? Yes. Are there lots? No. Okay. Most are going to be in this, quote, typical or average range of around 5'8" to 6 feet tall. That's going to be the, I don't know about the majority, but a lot. And then, you know, the further you go away from that, it becomes less or more common. Okay, or less common as you get farther away. Okay, and so we can kind of summarize this shape with something that looks like this. Okay, and this is where we get kind of the term the bell curve. Okay, or this would be, well, in statistics we would say this is unimodal and symmetric. Okay, so things like height is unimodal and symmetric. IQ scores is generally believed to be unimodal and symmetric. Okay, most common values are somewhere around average. Okay, and then as you go further and further above or further and further below, those values become less and less common, okay? Is that okay? And so, you know, instead of me drawing all of these kind of rectangles, I'm going to just kind of summarize these, use these simple curves to shape things. Okay, so we have unimodal and symmetric. We also have distributions that are, this is what we would call a skewed distribution. This is right skewed. Okay, it's skewed because there is what we call a tail. Okay, and this is a right tail. And if you need to remember whether something is right skewed or left skewed, okay, you just have to think, if you were to stab something, like a piece of meat, like skewer it, the side that you would use to do the skewering is on the right side, okay? So this is a right skewed distribution. So what does it mean to be right skewed, okay? So we would think, you know, where are the bulk of our values? The bulk of our values are kind of in this range right here. This is kind of the central area. Okay, so this is where your typical values lie. And what we have, so you know, let's just say this is, quote, the middle. And we'll talk about exact measures of middle on Monday. But let's say this is the middle. What this means is that we have some people who are very much above the middle, okay? So out here, you know, this is, if we have someone right here, this is a person who is very much higher than middle, okay? Much higher than the middle, okay? There might not be a ton of people who are that much higher than the middle, but there are people out there, okay? On the other hand, if we tried to go that far down below the middle, okay, however far this length is, if we try to go that far down below the middle, we would end up somewhere down here, and what we see over here is that no one is that far below the middle. Okay, so things that follow a right skewed distribution could be something like income, okay? So income, at least in our society today, is right skewed, okay? Probably the average income, something, I don't know, $55,000, something around there, okay? That's probably median income. Are there people who make $1 million a year? Yeah, okay, not a lot, but there are people who make $1 million a year, okay? $1 million is 900 something, you know, over $900,000 above average, okay? If we say average is 50, even if we said average is $100,000, which I don't think it is, but let's say we said the average is $100,000, someone making $1 million a year is 900,000 above average, okay? If we go 900,000 below average, that would take us to something like negative $800,000. Does anybody make negative $800,000 a year as what they're being paid? No, that would be impossible, if not illegal, okay? So what we have is, as far as income goes, you know, we have a middle over here. We have some people who are like way over here, highly skewed to the right, way above the average, okay? But we have no one that far below, okay? So, you know, income is, you know, very right skewed. Okay, and so we have that. Okay, if on the other hand, if that's right skewed, then what is this? Left skewed. All right, you guys have figured out the pattern. Okay. Okay, and so, you know, what's something that's left skewed? Perhaps scores on a relatively easy test. Okay, and so, you know, the bulk, if it's a relatively easy test, then, you know, the bulk of scores are going to be, you know, 90%, but you're not going to get over 100% unless there's extra credit, but then you're not going to get over the maximum score. Maybe that's 105%. Who knows? Okay, you can't get higher than perfect. On the other hand, you know, there will be a few students who score like 30% or 20%, okay? But not very many, okay? And if the average is something around 90%, you know, scoring down at the 20% is 70 percentage points below average, and no one's gonna get that 70 percentage points above average if the average is something around 90, okay? So that's left skewed, or, you know, you could think of whatever. I don't know. Okay, something like that. Those distributions were what we call unimodal. So the term unimodal means one peak. Okay, so you know when you talked about basic statistics in like middle school and things like that, you've probably learned about the mode being the most common value. So if you look at unimodal, the most common, there's only one value that is, or one range or area that is most common. So these are all unimodal, okay? So this one's unimodal because it's got one peak. This one's unimodal. Okay, this would be unimodal left skewed. This would be unimodal symmetric. Okay. We also have distributions that look like this. Okay, this would be a uniform distribution, meaning that there's no peak, it's just everything has about the same frequency, okay? So all values show up with the same frequency. And this would be something like, what is the last digit of your phone number? Okay, what's the last digit of your phone number? We would expect about the same number of people who has the number 4 as their last digit. We would expect about the same number of people as people who have the number 9 as their last digit, as people who have the number 1 as their last digit, okay? So we expect each of those digits or values to show up with about the same frequency there. So that'd be uniform. We also have bimodal distributions. Okay. So bimodal means 2 peaks. Okay. Now, keep in mind, we're just looking at one numeric variable, okay? So remember, we are still looking at just one numeric variable. And all this is saying is that even with this one numeric variable, certain values are quite common, other values are quite common, and you know, other values other than that are less common, okay? So here's an example, and this is, I have no idea what true values of this thing could be, but we could look at something like testosterone levels in humans. Okay? Now everybody produces testosterone, okay? Males and females, everybody produces some testosterone in your body, and you can go to the doctor and they can have you, I think they would take a saliva sample to measure your testosterone level, okay? And if we just looked at testosterone levels, I'm completely making up these numbers, so don't hold me to this, okay? So we might see values like 10, 12, 11, okay? And we might also see values like 75, 72, 70, and then maybe a value of 13, and a value of 14, and then a value of 74. Or something like this, okay? And this is just one numeric variable. We're just looking at testosterone levels. We haven't asked, are you male or female? We haven't asked any other questions. We're just looking at this one numeric variable. But based on our understanding of kind of biology, we can kind of guess which of these values correspond to men and which of these values correspond to women, right? Just by looking at kind of these numeric things. Now, we might not be completely accurate. We could be definitely wrong and things like that. But overall, we would probably see a pattern like this forming in our, if we were to create a histogram or plot this, okay? And so, based on our data, this might be something around, 70, and this might be something around 12, okay? And this is, the quote-unquote average testosterone level of women. And this here would be, the quote average testosterone level in men, okay? And so, this, someone out here would probably be, probably a man with high testosterone. Okay? Someone over here, this is probably a woman who has lower testosterone. Okay? And, someone over here, this could be, maybe a man with low testosterone, maybe a woman with high testosterone. We don't really know, okay? Okay? And so, again, the key here is we're just looking at one numeric variable. We're plotting that to see, what's common, what's uncommon, and we see kind of this bimodal distribution forming, where you have a common value for probably, one group, and a common value that appears for another group, something like that. Okay, so that would be a bimodal distribution there. Okay, and then if you have more than 2 peaks, we generally just say something like multimodal, okay? You could say trimodal, but more than 2 peaks, probably multimodal. Something like that, okay? I'm gonna run out of time. I got to talk about categorical variables, okay? All right, so when it comes to categorical variables, we displayed, I covered bar charts, right, on Wednesday, or I did not? Yes, no, maybe? Okay, well, I'll do it right here. Okay, so we could look at, like flowers, all right? And maybe, I don't know, I'm gonna make up flowers. We can have red flowers and pink flowers and white flowers. Okay, let's say these are, I don't know, some carnations, I have no idea. All right, and 20, 40, 20, okay? I'm just making up stuff. This is our beautiful bar chart. Okay, red, pink, white. We've got that, okay? Maybe some other species of flower, okay? We've got red, pink, and white. Okay, and let's say these are 30, 30, 30, okay. And so here, all right, and this is, I don't know, other flower, flower 2. Which would you say, which flower, I'm just going to call this flower 1 versus flower 2. Does flower 1 or flower 2 exhibit more variation in color? Flower 1 has more variation or flower 2 has more variation in colors? Okay, so the answer is flower 2 has more variation in color, okay? Okay, and you might say, well, how can that be? There's 30 red, 30 pink, 30 white, you know, there's 30, that shows up the same. There's no variation there, they all have the same value, 30. Well, that's actually the point. When we're talking about a categorical variable, if the different categories are equally represented, that is as much variation as you can possibly have, okay? Whereas if one category over here is, you know, has a majority or is more, quote, prevalent, then you have less variation or less diversity, okay? So, I mean, you can imagine going to 2 different schools, okay? And you can imagine going to a school where one race or one ethnicity is very heavily represented, okay? And then the other groups are very not represented very well, okay? And then you can go to another school where pretty much all races are equally represented, okay? Which would you say has more diversity? You'd say the school that has all of the races equally represented would have more diversity, whereas the one where only one race is represented has less diversity. The same type of thinking applies to categorical variables, where, you know, if you have red, pink, and white here equally represented, this has the most variation, whereas, you know, a situation where you have far more pink flowers than red or white, this has less variation, okay? It's, this concept of variation and spread will be different when we look at numeric variables, and we'll talk about that on Monday. But as far as displaying numeric or categorical data, this is what we have, okay? So have a great weekend, you guys. We'll see you guys on Monday.